In this video, we introduced the idea of the opposite of a vector, both geometrically and algebraically. Next, we introduced the zero vector as the result of adding a vector to its opposite. And finally, we defined vector subtraction as the addition of the opposite. And we learned to quickly visualize vector differences in a geometric way. So we start by defining the opposite of a vector v as a vector with the same magnitude but the opposite direction, and we call that negative v. Next, we imagine adding a vector to its opposite. So there's a vector v, and to vector add this to the opposite, we have to take the tail of the opposite vector, negative v, and attach it to the head of v itself. And then we draw the vector from the tail of the first vector to the head of the second. But the head and tail are in the same place. The result is a vector of length 0, and that's called the zero vector. Don't confuse the zero vector with the scalar 0. In order for the equation v vector plus the opposite of v equals 0 to make sense, the data type has to be the same on both sides of the equation. Those are vectors on the left. That's got to be a vector on the right. So that zero vector actually has two coordinates, and they're both 0. Next, we have a little note about scalar multiplication by negative 1. So given the vector v as a row vector 3, 5, I want to show graphically that negative 1 times v is the opposite of v. So it's useful to write this in the I hat, j hat notation. V is 3i hat plus 5j hat. So what's negative 1 times v? Just distribute the negative 1 to both terms and I get negative 3i hat minus 5j hat. Let's take a look at these vectors graphically. There's v. It has an x component of 3i hat and a y component of 5j hat. And there's negative 1 times v with its x component of negative 3i hat and its y component of negative 5j hat. And I can see that this produces a vector with the same magnitude and exactly the opposite direction. In other words, negative 1 times v is negative v, the thing that we call the opposite. Finally, I want to show algebraically that if I add v to negative 1 times v, I end up with 0. So there's v, and I add it to negative 1 times v. And all I have to do to add these vectors is just collect the like terms. And I have a 3i hat and a negative 3i hat. That gives me 0i hat. And I have a 5j hat and a negative 5j hat, and that gives me 0j hat. And again, I'm taking care to write this as a vector. It's the zero vector. It has two components that are both 0. Now we can use the idea of the opposite to define vector subtraction. So what do you do to find the difference between two vectors? V minus w? You add the opposite. This is exactly the same thing we do with scalars. If I told you to find the difference, 5 minus 3, I could say that I start with 5 and I add the opposite of 3. And of course I get 2 from that calculation. Well, now we can do the same thing with vectors. If I want v minus w, I think of it as v added to the opposite of w. And we have a good definition for the opposite of w now, so we can do this geometrically. The opposite of w is a vector the same length as w, but pointing in the opposite direction. And I'm trying to vector add that to the vector v, so I have to attach the tail of it to the head of v. And then I draw the vector from the tail of v to the head of negative w. I can also do vector subtraction algebraically. So in the next example, I have v is 2i hat minus j hat, w is negative 2i hat plus 3j hat, and I want to get v minus w. So I just plug in v is 2i hat minus j hat, and then subtract negative 2i hat plus 3j hat. Alternatively, you could say you're adding negative 1 times that quantity. We have to distribute that factor of negative 1. I have a double negative on that I hat component. Then we collect like terms. This gives me 4i hat minus 4j hat. And that's just an algebraic way of doing the same thing we did geometrically in the previous example. Finally, there's a very useful construction to remember about vector differences, and we use this all the time in physics. In this last picture, I have vectors v and w with their tails located in the same place. And if I do the same sort of construction that I did on the left, I take the opposite of w, and then I draw a vector from the tail of v to the head of that negative w, and that gives me v minus w. Okay, so there's nothing wrong with that, but the powerful new fact that I'm after here is that that vector difference I just drew is exactly the same as drawing a vector from the head of w to the head of v. That also gives you v minus w. So when you have two vectors located with their tails in the same place and you take their difference, it creates a vector pointing from the head of one to the head of the other. And I can verify that this makes sense by seeing that w and the difference v minus w are being vector added here because the tail of the second is stuck to the head of the first. And when I take w plus v minus w, the w's cancel, and I end up with a vector sum of v, which is exactly what I see in the picture here. So I like to use that little argument to remind myself which way it works. It's really going to pay off if you can remember that v minus w, provided their tails are in the same place, is a vector pointing from the head of w to the head of v. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.